Students, very warm welcome to the physics classes. I am Abhishek Kumar Chowdary, your physics lecturer. Today we are discussing a very interesting topic of physics called nucleus. Let's recall some concept of atomic structure. That was the Rutherford alpha ray scattering experiment. What happened in that experiment? See, there is a diagram over here. Alpha particle. And what are alpha particles? Alpha particles are the helium nucleus. Interestingly, in NEET 2019, they asked a question, what is alpha particle? And many students answered it wrongly, like alpha they took at helium as an element. Don't forget, alpha particle, they are helium nucleus. We are talking about nucleus. They are being bombarded on gold foil atom. On gold foil bombardment, and you can see the kinetic energy of that alpha particle that was used in this experiment in the year 1911. The kinetic energy was 5.5 mega electron volt. And what was experienced that time? It was experienced that the alpha particle was being repelled. Now, alpha particle being positively charged can only be repelled by a positively charged entity. Positively charged entity. It means there was something positively charged inside that gold foil atom, and that was termed as nucleus. So, nucleus is a positively charged, now I can say it positively charged body, but this was very much inside the atom, and the most interesting fact was it was core of atom, and you can see the radius of nucleus is almost 10 raised to power minus 4 times the radius of atom. Suppose if a classroom is taken as an atom, a pinhole in that classroom is the nucleus. So, nucleus is very small, and it is, again I am repeating, 10 raised to power minus 4 times the radius of atom. So, nucleus being core of atom, being very small entity, positively charged, its radius is such a small radius, is the topic of today's discussion. Now we will see what exactly is nucleus. Is there any structure available? Is nucleus is like we can study it like we studied atomic structure? What is the size? What exactly is the radius? What are the constituents in nucleus? To start with, our topic is atomic mass. See, atomic mass, the first point you can see, nucleus contains more than 99.9% of the mass of an atom. So, we can say that entire mass of an atom, almost more than 99.9%, entire mass of an atom is concentrated inside the nucleus. So, nucleus inside the atom is very heavy, almost we can say that nucleus is having all the mass of that atom. So, to describe that mass, to measure that mass, how that mass can be measured? So, if we will use suppose kilogram, we cannot use it as kilogram is a very large unit to measure mass. Suppose you are measuring length, you very well know that unit of length is kilometer. But suppose you are measuring length of your pen that you are using for writing it, can you measure that length of your pen in terms of kilometer? Obviously, you won't. You can, but you will not. Similarly, mass of nucleus, atomic mass, this is very less. So, measure it, we are just taking another unit that is called atomic mass unit. What is atomic mass unit? What is AMU? It is being denoted by U, dear students. This is 1/12 the mass of carbon 12 atom. You are taking mass of carbon 12 atom, and 1/12th part of that is called 1 atomic mass unit. So, what is the mass of carbon 12 atom? You can see the data here. 1.992647 into 10 raised to power minus 26 upon 12, that would be 1.6605 into 10 raised to power minus 27 kg. You have to memorize this data. This is the conversion of one atomic mass unit into the kg. Moreover, accurately atomic masses are being measured in spectrometer, mass spectrometer, and from there we accurately measure the masses in atomic mass unit. Also, this mass you can see is 10 raised to power minus 27 kg, means as compared to the kg, this is a very small mass. Now we will discuss constituents of a nucleus. What is there inside the nucleus? And the very first constituent is proton. What is proton? We all know that in a very basic manner, proton is a positive charge. There is a mass also, but that is the properties, like charge is 8, mass is 8. This is of property. These are the properties of proton. But the question is, what exactly is proton? Why it is inside the nucleus? To understand this, we will first start the concept of, you can see, isotope. See, atomic mass of most of the elements are almost the integral multiple of the atomic mass of hydrogen. Integral multiple almost of atomic mass of hydrogen, but there are some exceptions as well, and the exception is, you can see here, isotope of chlorine, the atomic mass of chlorine. So first we will start with the definition, then you will understand what is the proton and how we are deciding the atomic masses of elements. See, isotopes are same chemical behavior but different atomic masses. Same chemical behavior. Let me tell you, chemical behavior, they are being decided according to the electronic configuration. So if the same electronic configuration is there, it means the chemical behavior is same, and you very well know that if the electronic configuration is same, the place in the periodic table is at one place. All element with same chemical behavior, it means they are at the same place in the periodic table. At the same place in periodic table, in Greek, at the same place is called isotope. So when we say isotope, it actually means at the same place inside the periodic table, but various different atomic masses. Okay. Now see, there are two isotopes of chlorine. So when I am saying chlorine, that means that chlorine that you see inside the periodic table at one place, but that chlorine has two different atomic masses. What are these atomic masses? These are 34.98 U, means atomic mass unit, with relative abundance 75.4% and 36.98 atomic mass unit with relative abundance as 24.6%. So we will calculate the actual atomic mass of chlorine as weighted average of these two. How to calculate? What is weighted average? See, atomic mass of chlorine 75.4% for 34.98 U, 24.6% for 36.98 atomic mass unit. Since we are calculating in percentage divided by 100, you will calculate a value of 35.47 atomic mass unit, which is called atomic mass of chlorine. But this atomic mass has two isotopes, and according to their relative abundance we calculated this. Okay, now as we know what the isotopes are, let's see, there are three isotopes of hydrogen atom called hydrogen, deuterium and tritium. You can see their respective atomic masses as well, almost in the ratio of 1:2:3. Hydrogen, deuterium and tritium. Tritium is kind of unstable and we don't find it in nature, although we can make tritium in laboratories. Now see the lightest one. The lightest one is hydrogen 1.0078 U atomic mass unit, and proton is nucleus. Proton is nucleus of the lightest atom of hydrogen. Why I am saying lightest? Because hydrogen has got 3 isotopes. Obviously these 3 are of different masses. So the lesser mass, the lightest one is hydrogen, and proton is nucleus of that lightest hydrogen atom. So what is proton? Now we are very clear what exactly is proton. Proton is nucleus. Nucleus of what? Nucleus of lightest atom of hydrogen, and its relative abundance is 99.985%. A very important data, 99.985%. Mass of proton is, the data you all know, but how to calculate that? The concept is mass of proton is mass of the lightest hydrogen atom minus mass of electron. If we will put the data for these two, we will get mass of proton as 1.00727 atomic mass unit, and to convert it into kg, we know that conversion of atomic mass unit to kg. So in kg we found it to be 1.67262 into 10 raised to power minus 27 kg. We know what exactly is proton. Suppose there is a question asked in NEET, they might ask you, what is a proton? There is an option, it's a positive charge, but this would not be a right option. The right option would be proton is nucleus of the lightest hydrogen atom. We know that proton has some mass, and we have just calculated that mass as mass of that lightest hydrogen atom minus mass of electron in atomic mass unit. Now in Rutherford's experiment, the alpha particle was repelled by nucleus, hence the nucleus must have some positive charge. So we are now calculating charge on proton. See, atom overall, suppose this is an atom. So this atom overall, we all know that is neutral, isn't it? It is neutral. There is no net charge. Having said that, we also know that charge on electron is minus ZE, where Z is used to denote the atomic number, minus ZE. So if atom is totally neutral, there must be some equivalent positive charge. So total charge of proton, I am not talking about charge on one proton, total charge of proton would be plus ZE. So obviously when we will use the quantization of charge for one proton, the charge is E, which is equal to the charge on one electron. So it's 1.6 into 10 raised to power minus 19 coulomb. This is the charge on one proton. We have discussed the first constituent of the nucleus, and that was proton. Now we are aware of the mass of proton, charge of proton, and what exactly is proton. Now moving to the second constituent, the neutron, which is a neutral particle. The very first question is how we knew that there is a neutron. What was the logic? The logic was very simple. when you will see the isotopes of the hydrogen atom, that is the hydrogen, deuterium and tritium, I said that the atomic masses, they were in the ratio of 1:2:3, although the charge is that of one proton only. So, if there is one proton, then mass would have been in a ratio of 1:1:1, but this is not the case. The charge is in that ratio 1:1:1 for hydrogen, deuterium and tritium, but mass is 1:2:3. It means some mass is being adding up without the addition of charge. It means some neutral particle is there which is not adding up to the charges but adding up to the masses. The discovery was done by James Chadwick in 1932, and for that he also got a Nobel Prize in 1935. See, if I will go into the experiment that leads to the discovery of neutron, it was bombardment of alpha particle on beryllium atom. When alpha particle was bombarded in year 1930, the experiment was being done. This was alpha particle bombardment on beryllium atom. In that experiment, some radiations was emitted. The radiation were emitting, and that radiation was the neutral radiation. At that time, neutral radiation was only photons. Before this experiment, neutral radiation was assumed to be that it is photon. Okay. Now, photons energy and the beryllium atom experiments radiation, that energy was not matching. Photons energy was usually very high. Then what kind of that radiation was? That was a neutral radiation, and on the basis of that neutral radiation, neutron was discovered. Let me tell you the mass of neutron, 1.00866 atomic mass unit, and we know now how to convert that into kg. So, this is the kg mass. Now, see the free neutron characteristic. Free neutron means we are not talking about the neutron inside the nucleus. Free neutron, it is unstable and it decays. It is unstable and it radially decays into proton, electron and antineutrino. Let me write it for you. It decays into proton, electron and antineutrino. Proton, electron and antineutrino. Antineutrino is again a neutral radiation. Mean life, average life for free neutrons are 1000 seconds. Such a short span of life they exist. But when we talk about the neutron inside the nucleus, they are very much stable. Now we know about the constituent of nucleus, that is proton is there, neutron is there. So let's see what is now the overall composition and how to denote them. Z is the denotion of atomic number, that is number of protons. Capital N is number of neutrons, and capital A as mass number that is Z plus N, number of protons plus number of neutrons. This is collectively called nucleons. Protons and neutrons, they are found inside the nucleus, so they are collectively called nucleons. Number of nucleons means the mass number. Let us see the denotion. Denotion, suppose X. What is X? X is the chemical name of that element, any element. For example, if I am taking gold, Au, in place of X, you can see an example, I have written Au, gold, that is the chemical name of gold. A and Z, in the top we write the atomic mass, in the bottom we write Z, that is the atomic number or number of protons. You can write on a cross side also, same side also. For example, now overall you can see gold 197.79. Let me tell you a very interesting fact about gold. It has got 32 isotopes. 32 isotopes from 173 to 204, and this whatever you are saying is the weighted average. 32 isotopes from A equal to 173 to A equal to 204. Now our next definition is that of isobars and isotones. Isobars, nuclei having the same mass number and different atomic number. Since atomic number is different, obviously the electronic configuration is different, and electronic configuration is different, it means different chemical properties. So they are not at the same place in the periodic table. See some example, 1s3 and He32. You can see at the top the mass numbers are same. Lithium 7, beryllium 7, again at the top 7 mass number are same. But one interesting thing that you can see in this example, A is 7, Z, that is number of protons, is 3. What is the number of neutrons? It's 4. We can say 4 neutrons. In the same way, here mass number is 7, atomic number is 4. Now what is the number of neutrons here? We can say 3. It means 3 and 4 are getting exchanged. You can see here 3 atomic number for Li, 3 number of neutrons for beryllium, 4 atomic number, that is number of protons for beryllium, 4 number of neutrons for lithium. So they are getting their number of protons and neutrons exchanged. Such nuclei are called mirror nuclei. Such nuclei are called mirror nuclei. Now we will see the definition of isotones. Nuclei having same number of neutrons, as simple as that. And what is number of neutron in symbolic manner? A minus Z, mass number minus atomic number. Same A minus Z means isotones. We can see an example, 1s3 and He42. Difference that A minus Z we are getting 2, 4 minus 2 we are getting 2, they are called isotones. Till now we have discussed the composition and the constituent of a nucleus. Now we are interested what exactly is the size of that nucleus. For that, again we are recalling the Rutherford's alpha particle experiment. In that experiment, the alpha particle was stopped almost at a distance of 4 into 10 raised to power minus 14 meter from the nucleus, with obvious reason of the nuclear repulsion. Let me tell you one thing, Rutherford's experiment was solely based on the Coulombic repulsion between the nucleus and the alpha particle, although there might be various reasons for that stopping also. But Rutherford only considered the Coulombic repulsion. See, the minimum distance of alpha particle from nucleus of gold foil, this is called closest distance of approach, and which is calculated as the Coulombic forces work and loss in kinetic energy, that we will discuss in a separate topic later. But as a fact, in Rutherford experiment we can take this data. The minimum distance, this was the gold foil nucleus, this was the alpha particle maximum point achieved, and the separation between these 2 points was called closest distance of approach, which was 4 into 10 raised to power minus 14 meter. Having said that, one thing is very clear, that nucleus is less than this, at least nuclear radius is less than this at least, which was further calculated as formula R equal to R naught A raised to power 1 by 3. This is the formula for calculating nuclear radius, which is clearly depending upon A. R naught being a constant, 1.2 Fermi meter, 1.2 into 10 raised to power minus 15 meter. Now, if using this formula, we will calculate the volume 4 by 3 pi r cube considering the spherical shape of nucleus. You can clearly see that this volume is proportional to A. And density, what about density? Mass upon volume, A upon this volume, A cancelled. So, all the quantities in this density they are constant. The proportionality power you can see on A0. So, the nuclear density is independent of A. It does not matter of what element you are calculating the density. Nuclear density is constant for all the nuclei, and the value is 2.3 into 10 raised to power 17 kg meter cube per meter cube, and clearly see the order of magnitude. Can you see order of magnitude? 10 raised to power 17. You can get an idea how dense is the nucleus. One bottom line I am repeating again, nuclear density, it is students independent of A. Doesn't matter of what nuclei, density remains constant. Density is very high. Such a high density is found in neutron stars, white dwarfs. Is it not a frequent density that we encounter in our daily life? On that basis, density, nuclear density basis, the radius of nucleus is being decided, and the term is, we will see the definition. Radius of nucleus is defined as the distance from the center where the density falls to half. See, density R graph you can see, density from rho naught to rho naught by 2, and it has fallen at a distance of radius. So, what is nuclear radius? Distance from the center where density has becomes half. So, R equal to R naught A mass number power 1 by 3. If on this basis you will see a numerical, we have to compare the radii of nuclei of AL and TE. What you have to compare? Radii, AL and TE. Clearly see the mass number 27 and 125. And what is the formula? Proportionality to A raised to power 1 by 3. RAL upon RTE, radius 27 upon 125, 1 by 3. Answer is 3:5. So today we have discussed the basic definition of nucleus, its constituents, and the nuclear size, radius of the nucleus. There are many interesting facts yet to come, like binding energy, the Einstein's experiment, the mass defect, and then radioactivity. So in our next class, we will be discussing that binding energy and mass defect. Stay happy and happy learning. Thank you. Bye-bye.